Hi everybody, this is Dr. Kat Vlies with Central New Mexico Community College. We're going to continue with the skeletal muscle physiology, and in this video I'd like to focus on what is happening at the level of the motor end plate, where we're going to see something called a motor end plate potential, and also the action potential. So we're going to take a look at the motor end plate potential, sometimes just called the end plate potential, as well as the action potential. So I'm going to use a very simple sketch this time. Based on your knowledge from previous videos, I'm hoping this is going to make sense. So let's say that once again that on this side we have our axonal terminal. I'm going to keep this a bit smaller than usual. And let's say that here is our motor end plate. And here we have the rest of the sarcolemma, and possibly here we're seeing a T-tubule, like so. Our cell is at rest. It has typically a resting membrane potential of about -90, meaning when we measure the difference of the charges across the cell membrane, we find that that value is around -90 millivolts. And the minus reflects the fact that the inside of the cell is less positive compared to the outside of the cell. And again, what I'm working with right now is, of course, our muscle cell, and here I'm going into our T-tubule. And this would be the same case on this side of our T-tubule. And don't forget that over here we have our extracellular material, and that extracellular material continues down into the T-tubule. We also have extracellular material separating our motor end plate and then the rest of the sarcolemma into the T-tubules. So over here, where the motor end plate is, so this is our motor end plate. This is the region of the sarcolemma that is very convoluted, so that we increase the surface area for the number of acetylcholine receptors that we need here. Remember, these acetylcholine receptors are proteins that will change their shape, their three-dimensional shape, the moment acetylcholine binds to them. So if we have our acetylcholine being released here by our axonal terminals bulb, that acetylcholine will eventually bind to all of these receptors located in the motor end plate. These receptors that we find in the motor end plate respond to the binding of a chemical, which is our acetylcholine neurotransmitter. And so therefore, remember, those ion channels are chemically gated ion channels. So the receptors have a dual function. They bind acetylcholine, but they also are capable of allowing for the passage of ions. Chemically gated ion channels are very crowded in this motor end plate area, where acetylcholine can reach those channels, which are also receptors. Allow me to indicate these channels with the letters C everywhere to remind you that these are chemically gated ion channels. And remember too that they're going to allow for primarily sodium to rush in and some potassium to rush out when acetylcholine binds. As we get away from that motor end plate, we're going to see that we see more and more of a different type of ion channel, which we call a voltage-gated ion channel, all the way down the T-tubules. And they're very crowded. And they're located, again, in the membrane of our muscle cell, better called the sarcolemma. So these V's are representing our voltage-gated ion channels. Let me switch pens because this one is not writing extremely well. So C for the chemically gated ion channels. Okay, now within the voltage-gated ion channels, as you know, we have those that are going to allow for the passage of sodium and those that are going to allow for the passage of potassium. Always, sodium will rush in, no matter where we are, sodium will rush in, while potassium will always move out, whether it's through the chemically gated ion channels or the potassium or the voltage gated ion channels. It doesn't matter. And this is because the direction is determined, the direction of the flow of the ions, as you know by now, is determined by their concentration gradient. Your concentration gradients, just as a quick refresher, you have a lot more potassium on the inside of a cell compared to its outside, and vice versa. You have a lot more of the sodium on the outside of the cell than you have on the inside of the cell. So we're focusing today just on sodium and potassium, even though calcium also plays a role in our neuromuscular junction, but it has different roles. Calcium in our neuromuscular junction does not play a role in the passing on of an electrical signal. Okay, so when all of this sodium starts to rush in, more so than potassium rushes out, at the level of the chemically gated ion channels, that is where the motor end plate is, what's going to happen is that little by little the inside of our cell membrane is going to start becoming more and more positive compared to the outside of our cell membrane. So let me just indicate this really quickly. This gets messy, unfortunately. So now we see that there's a reversal in the polarity. So now let's really make some more sense out of this. Remember that I said that at rest, the resting membrane potential of a skeletal muscle cell tends to be around minus 90 millivolts. We're now bringing in mostly positively charged sodium particles, and therefore we're going to see that little by little we're disturbing our resting membrane potential, and we're going to see that this very negative number of minus 90 is going to become less negative. So an example of that could be minus 89 millivolts or minus 88 millivolts, etc. So we're going to see that our resting membrane potential is turning into what we better call a graded potential. And this graded potential can continue to build up and get stronger or I should say, yeah, we'll call it stronger and stronger, because what is happening here when all of the sodium, or primarily sodium, is moving in is a process we call depolarization, that reversal in the polarity of our cell membrane. Now, the more acetylcholine binds and the longer the ion channels stay open, the more graded potentials are generated, and the more that all of these graded potentials, waves of depolarization, start to merge together. So the way to visualize this depolarization that is occurring everywhere where acetylcholine is binding is that we throw a rock in a pond of water, and where nearby where the rock hit the water, the waves are the strongest, and then further away from where the rock hit the water, the waves are not as strong. But if we put in, or we throw in multiple rocks into that pond, all of those waves begin to merge together and can actually become stronger. And that's exactly what we see happening here. From there, the term a graded potential. Graded meaning that it can be of different strengths. Okay, so the term graded always means that there are different gradations of strength, meaning we can have a change of 1 millivolt, 2 millivolt, 3 millivolts, and even much more. So if we have enough graded potentials being generated at the motor end plate, we're eventually going to create a very strong depolarization. And our goal indeed is to eventually reach a depolarization of about a change of 15 millivolts, which brings us to eventually around minus 75 millivolts. So this is a change of about plus 15 millivolts. So plus 15 to plus 20 millivolts is needing to happen in order for us to see the opening of our voltage-gated ion channels. Okay, now before we go to the voltage-gated ion channels, let me give this graded potential a more specific name. In our body, especially in the nervous system, we're going to see that there are graded potentials occurring as well, not just on our muscle cells. And depending on where these graded potentials occur, they get specific names. So our graded potential at our motor end plate is going to be called an end plate potential or a motor end plate potential, but very often we leave the term motor off. So an end plate potential is a graded potential at the motor end plate of a skeletal muscle cell. And it results from the binding of acetylcholine to chemically gated ion channels, which therefore are going to allow for primarily sodium to rush in. We bring in primarily positive particles, and consequently we see reversal in the polarity. And this we call depolarization, which keeps building up and getting stronger and stronger, such that eventually all of these end plate potentials merge together strong enough to and create a strong enough depolarization to where they create a change of about 15 millivolts in our resting membrane potential. Now we've hit what we call threshold voltage. So when we have this change of about 15 millivolts in our resting membrane potential, we have reached something that we call threshold voltage. And what that means is that this is the minimum amount of change that must happen in our resting membrane potential to trigger the opening of voltage-gated channels. So these voltage-gated channels need a certain change in voltage, and then they open. The first voltage-gated channels that will open when we hit threshold voltage will always be our sodium ion channels. So the first ones that will open will be sodium voltage-gated ion channels, and sodium will start rushing in. So now we see that right next door to our motor end plate, we continue to see depolarization occurring. But this depolarization is going to maintain its strength. In other words, when we reach this threshold voltage of depolarization, it is going to open up so many sodium voltage-gated ion channels, one after the other, that we see a very, very strong depolarization, much stronger than the minus 75. And we'll see how strong later down the line when we get to the nervous system and we really analyze what action potentials are all about. But the point is that once we have opened our first sodium voltage-gated ion channels, it triggers the opening of more sodium voltage-gated ion channels. And that triggers the opening of even more and more and more. And you can see that we're looking here at a positive feedback mechanism. So the depolarization very rapidly in the form of an action potential starts to move down into the T-tubules. Now, this depolarization as it moves, and this is now going to be impossible for me to draw unless I start erasing, But this depolarization, when it moves, and let's say it reaches over here, it is going to quickly be followed by the closing of the voltage-gated ion channels and instead the opening of our potassium channels. So as we're continuing to depolarize in this direction, because we continue to open up sodium voltage-gated ion channels, on its tail of depolarization, we're going to see that the voltage-gated ion channels in this area begin to close, and instead the potassium voltage-gated ion channels open, and we therefore see the process of repolarization occurring. And of course that would mean that we return back to resting conditions, while the rest of the sarcolemma is becoming still depolarized. Remember that potassium has a concentration gradient that is going to allow it to leave the cell. So when the cell is depolarized, meaning that the inside is much more positive compared to the outside due to the influx of positively charged sodium particles, and we now shut the channels that allow the influx of sodium, but we open up potassium channels, then potassium can leave through those channels, and it takes with it positive charges. So all of the positive charges that were brought in are now sent back out. Via different ions, we bring in positive charges via sodium, and we get rid of them via potassium, but we manage to restore the electrical gradient. We manage to get back to our resting membrane potential. And so this happens all the way down our T-tubule, and remember, we call that the depolarization with the repolarization following. That is our action potential. So our action potential consists of depolarization followed by repolarization, and that action potential goes all the way down our T-tubules. Think of it as a body of water that follows the whole cell membrane. And don't forget that the cell is a three-dimensional structure, so it's coming towards me and towards you. And again, it's a body of water on both sides of the membrane. Once that action potential goes down the T-tubules, it triggers the release of calcium from the terminal cisternae. The calcium binds to the troponin complexes of the thin filaments, and we see that cross bridges can occur and the sliding of the filaments can occur. Okay, one last thing to address before we wrap up here, and that is, okay, so once our cell membrane has repolarized, because our action potential as it travels will depolarize the membrane and also repolarize it. And let's assume that we do not have any more acetylcholine binding anymore. That's going to stop the opening of those first sodium voltage-gated ion channels. We still have a problem, don't we? Because even though we have restored our electrical gradient, and this will happen over here as well because ions will leak in and out along their concentration gradient, so eventually we fix things over here as well. What is still a problem is that we have way too much sodium on the inside and not enough potassium, and vice versa on the outside of the cell. So while we might have fixed our electrical gradient back to resting membrane potential, but we haven't fixed the concentration gradient. So in addition to all of these chemically gated ion channels, voltage-gated ion channels, and some channels that are always open called leakage channels that help us get back to rest here at the level of the motor end plate, we have a fourth type of channel, and those are our ion pumps. And for sodium and potassium, of course, those are your sodium-potassium pumps. So let me add these really quickly in our figure just to be sure that all of you remember what the sodium-potassium pump does. I'm just going to draw it as a big oval here. The sodium-potassium pump uses ATP, so it hydrolyzes ATP the way we've learned in the previous video. It's going to break down ATP into ADP and PI, and the energy that is released is going to allow this protein to pump ions against their concentration gradient. So now we're going to see that instead of sodium following its concentration gradient, it's going to move against its concentration gradient. So sodium, in this scenario where we are looking at our sodium-potassium pump, the sodium is now going to move out of the cell towards where there is a lot of sodium normally. And the opposite for potassium. For potassium, we're going to see that, and I'll use a dotted line just to show that it's a different ion. For potassium, we're going to see that it's going to move into the cell against its concentration gradient. Remember, there is always already a lot of potassium inside of the cell. And so this is how a cell restores its concentration gradient with the help of sodium-potassium ion pumps. All cells have additional pumps, by the way. You might want to start thinking about the fact that we also need calcium ion pumps in our axonal terminal, and we will probably also need calcium ion pumps in our terminal cisternae, because without those pumps, we could not reclaim the calcium that was lost from the terminal cisternae, or the extracellular material here could not reclaim the calcium that rushed into our axonal terminals. So calcium and sodium, potassium, and there are even other ion pumps play a very crucial role in our body. So this is a summary of how chemically gated ion channels as well as voltage-gated ion channels play a role in our body to allow for the generation of graded potentials, which can then lead to what we call an action potential. And what these graded potentials do is they all merge together, and I'm going to give you one last word to learn, and when they do that, we say that they summate. Graded potentials summate, they all add up to eventually reach that threshold voltage, and that's the voltage of that's meaning about a change of 15 millivolt in the resting membrane potential that will open up our very first sodium voltage-gated ion channel. If the term voltage-gated ion channel is not really clicking for you, you can replace it with the term electrically gated ion channels. Thanks for watching. Till next time.